everyone, I'm Will from Maths Squared. Today we're going to look at a new topic known as differentiation. Differentiation belongs to a part of maths that you may have already heard of called calculus. Calculus sounds really challenging at first, but as we'll see over the course of these short lessons, it's not as bad as it looks. Now, before we get into the lesson today, make sure you check out the website from the link on the screen to access further resources, notes and become part of the Maths Squared community. Also, make sure to subscribe to see more videos on all things maths and physics. Okay, differentiation is all about gradients and specifically the rate of change of variables. From our previous studies of straight line graphs, like the one on screen, how might have we calculated the gradient? Well, we'd take 2 points along the line, work out its rise, which is the change in its y coordinates, and divide it by its run, which is the change in its x coordinates. The gradient, which you may remember being called m, is the rise divided by the run, or the change in y coordinates divided by the change in x coordinates. What would we do then if we had a nonlinear function like this? As you can see, the gradient is going to be different at every point along this function. What if we zoomed into a tiny part of this line? Can you see that the further we zoom in, the more this looks like a straight line that we dealt with previously? Now we can work out the gradient just as we've done before. We can call the change in our x coordinate h, and define our first y coordinate as f of x, then our second y coordinate will be f at x plus h. Now exactly as we did for straight lines, we can work out our gradient as the change in y, our rise, and divide it by the change in x, our run. Can you see that this approximation will become better and better the smaller h gets? The smaller this section becomes, the closer we can approximate the line to be straight. So we're going to restrict or limit h to 0. So finally, that leaves us with this expression here. Note that we write dy and dx rather than the delta y and delta x. This is to show that we're differentiating. Let's look at an example. Here we have the function f of x, which equals x squared. So our f of x plus h is going to be equal to x plus h squared. You should feel comfortable expanding brackets in this way, but if you don't, I suggest you watch what I do here and then do some practice algebra questions. So after that, we're left with this expression for the function at x plus h. Of course, we have f of x from the question. We can then plug both of these back into our formula. We can now simplify our expression. We can start by cancelling out the x squareds, then divide by a factor of h from top and bottom, and then finally deal with this limit of h to 0. The h within our expression will of course tend to 0. However, the 2x is independent of h, so this will stay as it is. Therefore, the derivative of x squared is 2x. Here are 3 questions for you to have a go at. Pause the video here and give them a go. Here are the answers, check them against yours. If you got any wrong, go back and rewatch some of the video, or leave a comment and I can explain further. So here's the takeaway message. If y equals x to any power, to the power of n in this example, then the derivative dy dx can be calculated by timesing by the power and then dropping the power by 1. So that brings us to the end of this first lesson on differentiation. Leave a like and subscribe to see more lessons like these. Once again, check out mathsquared.org to boost your maths progress. Thank you, bye bye.